Hi there. So in this video, let me talk something about lift and drag coefficients and forces. So this is very important because I didn't do it when setting up the cases because it's a symmetrical geometry who has this one, but when we're doing airfoils or something else, it is important. So let me show you this slide here. So one thing that remember that lift and drag, those are forces, are perpendicular and parallel to the common flow. Okay, so the lift force is perpendicular to the incoming flow and the drag force is parallel. So if you are running simulations, okay, and you are changing, let's say, the angle of attack, and you are doing that modification by changing the inlet velocity, you will need to rotate the reference axis. This one I call it here lift dir and drag dir. This is a simple rotational matrix in order to compute your forces in the right axis. If you don't do this, you will get the forces but in a different reference frame, which it will be wrong, will give you the result, the wrong results. But it's not because the computation is wrong, it's just because you forgot to do this rotation that you can do it a posteriori. Okay, so let's say that if you rotate this 5 degrees, or you inlet velocity 5 degrees, you put here 5 and rotate using my reference system, now YX. If instead of rotating, changing the angle of inlet velocity, and your velocity is always horizontal, and you just change here the angle of attack, the geometrical angle of attack, you don't need to do anything because it's always 1 0 0 for drag and 0 1 0 for lift. Okay, so this is very important, and this transformation you must define it in Fluent and also in any other solver because it's not computed automatically. And just to show you that probably later we do airfoils and we'll see better that. But for instance, if we go back to the cylinder case, and this is my mistake, I didn't show you this, is you go and let me show you here. You have in results. So this is the 3D case, okay, then I will show you something in the 2D case. So see here that you have forces, and you can compute it here, print, these are the forces in that reference axis. But if you change this one, so let me put a 1 here, see that your coefficients, so look at that, you have, okay, coefficients, okay, look at that, they are different. And if I change this one, see that they are different because I have different reference systems. So this is important to do, okay? And in this case, as you go here when you are defining your reports, see that you have CD. As you open this one, CD, my drag coefficient is in the X direction. My velocity is entering like this. This is okay. It's 1 0, but see that I left this 1 0. This is a 3D case. 1. This is wrong. This is what will give you the wrong forces. So let me go back here to show you a computation. So 1 0 0 here. 1 0 1, the one that we're doing. See that these are your coefficients. Now the right one is this one. Okay, so be careful when doing that. Here I forgot my mistake, but always this is something that you need to check. So in this case, the right one will be like this, and then also for lift you should do the same. So see that I left this one to 1. So here now let me go back. So lift is 1 0 1. So this is the one that you get in the right cis transformation, and this is the other transformation. So be careful with this transformation. So the other way, for instance, what happens, so is you decide to run the case, and if you are running the case, and instead of changing so here you can change you see that you have normal to the boundary, but you can give magnitude and direction. So if you decide to change the angle of attack by changing the inlet velocity, you need to add this transformation. But instead, it's always your velocity is aligned with your reference system. You don't need to do it. Okay, so this is always check this one. Okay, be careful in this case. I didn't comment about this. I just realizing when checking everything that I didn't add this comment. So always control here. You have your force vector, okay? So you need to define your force vector depending on your reference system. My choice I prefer, so when you do this one, honestly, I prefer to rotate the geometry. That will imply that you will need to do different meshes, but if you have a good parametrization, it's not a problem, okay? I don't like to rotate this one because also requires changing some other boundary conditions. So in this case, for instance, you rotate that one, you will change this one, but also here you need to give the inlet velocity here and this to become outlet. So you have to be careful with that. So that is the small warning that I wanted to give you. So all the results that you have here, they're okay. But the only caveat that I want to give you here is that you don't need to rerun. This is okay, but you need just to correct these results. So for instance, let me open CL. If I plot this one and axis, okay, so I don't have the complete history. Well, let me go to the here. So in the I have also a 2D case is exactly the same, by the way. So let me go here to the case, and if I open let me load the CD here. Okay, open this one, and if I plot this, so see that I have this. Okay, but if you forget to do that correction, you just need to multiply this by the transformation. Okay, there is no need to rerun that. Okay, so be careful with that. And the last thing, so that is applies also for 2D, but in 2D, okay, let me show you. If I go here into the, see that the third dimension is comment is not available. So here there is a 1, but it's a 0, so there is no problem. Okay, it's 1 0. These are the two that you are using. The other thing that I would like to mention here, I'm probably when plotting these forces, and let me go here and let me go to this plot. Okay, axis and plot. Okay, so here, so see that is some people don't like this when you are running, and see that if you are running, and see that you have this scale that are automatically chosen by Fluent in all these plots. Okay, but if you don't like this scale, the axis, the minimum and maximum, the axis, you have seen that can be changed now when we were doing the FFT. But to do it in your monitors, okay, let me stop here. So for instance, let me do it here in CD that you don't see well. So see that when you create your monitors, and you decide to plot, here you have the other option, add the plot. So for instance, I want to modify the CD plot. You click here. Okay, you select here and change axis. So let me see that I want to change this one, and I want from 0 to 2. Apply. Check that is okay. And then the start calculation. Now you have this axis that you see better your results. You can do the same here, okay, in all the plots, okay. So for instance, I don't like this imbalance here plot. Let me stop this. Okay, so the imbalance, I have it here. Select your value, axis, and then Y. And let me put that this goes from, let me say that go from 0, 1 to minus 0, 1 to 0, 1. Apply. And you plot, and then you have your axis. Okay, so see that is basically 0 the value, okay, as we should expect. So calculate, and you have that. Okay, so you can change all your axes in the plots here. Okay, so if you're running and you don't like the axis, you have something smaller, larger. So for instance, let's do it again for the Y plus this one. So let me stop here. Okay, so I'm working in the 2D case, but it's the same for the 3D case, nothing changed. So this is the Y plus average, this one. So let me say that you select that quantity, the axis, it is the y-axis, and then you go that I want from 0.2 to 0.4. Put it here, and put it here. Apply, plot, and you have your axis there, okay? So probably 0.3, apply, plot, and you have it, and you keep running, and you have your new axis there. No problem. So this is the small correction that I wanted to do it. So later when we work in the airfoil cases, you will see this transformation better, but always control that when you are computing forces and you have different reference system or the wind reference system, you need to add this rotational matrix that basically is this. Okay, it's a simple rotation matrix, and it depends on the reference system that you are using. So in this case, I'm using X, Y like this. If you have different reference system, you will need to do this matrix rotation. So that's all. Thank you for your attention. See you in the next video. Bye.